we are welcoming back Professor of Geometry, Alain Goriely, to give the first of his 6 lectures this year on the geometry of nature. And his lecture tonight is entitled, I can't read that backwards, The Shape of Hands, Symmetry, Chirality and Handedness. Thank you, Alain.
Thank you very much, Sarah. It's always great to see you. It's great to be back here also. So indeed, today I'll be talking about symmetry, chirality, and handedness. It's a problem that I've been thinking maybe for, let's say, about 30 years. And when I'm thinking, I've been a bit obsessed, as my wife, Nita, who's sitting with us today, can tell you. And indeed, as Sarah mentioned, it's a series of lectures dedicated to try to look at various aspects of geometry and nature. But let's go straight into it, and let me tell you about chirality. So it's all about hands. Chirality is a property of the hand. The word comes from chair in Greek, which means hands. So what about hands? Well, I'm going to need your help today. This is my right hand. And I want to make sure that you can locate your right hand. So please show me your right hand. Make sure that it's not that easy. Both Sigmund Freud and Richard Feynman said they had problem directly thinking about the right hand. They had to think of the size they were writing in order to locate it. Okay, this is my right hand, and this is the mirror image of my right hand, as you can see. And if I put them next to each other, the mirror image looks pretty much like my left hand, so let's pretend it's that. And to start the reflection, I'm going to quote Immanuel Kant, who says in 1783, "What can more resemble my hand than its image in the mirror? And yet I cannot put such hand as is seen in the mirror in the place of its original." He says, these are so similar, I can't see the difference between them, but I can't also superimpose them. Okay, so the idea is that whatever you do, you can try to move your hand and all that, you cannot put together, and you know that because your left glove doesn't fit on your right hand. So this idea was eventually formalized by Lord Kelvin in 1893. And he says in this talk, and we have definition from him, he says, "I call any geometrical figure or group of points chiral," and says it as chirality, the property of being chiral, "if its image in a plane mirror, ideally realized, cannot be brought to coincide by itself." So it's exactly this notion. I cannot put it together. And to be more precise mathematically, what that means is that I can do any translation and rotation in space, and yet I cannot superimpose the point-to-point on that hand. Hence, this object, my hand, your right hand, or my left hand, have the property of being chiral. So this type of transformation in mathematics is called a rigid body transformation. It's a translation plus a rotation. Okay? So if an object is not chiral, it's achiral, and it has the property of being able to superimpose itself. You take a sphere and you take its mirror image, obviously you can put it together. And there are plenty of achiral things around us. If you look at this chair, for instance, clearly there is a mirror symmetry. So when I take the image, it's essentially flip it on itself. I don't even have to move anything. If it's a mirror symmetry, automatically the object is achiral. And chairs have this type of chirality and many objects around us because mostly the human body is also achiral. It has a mirror symmetry, and here the Vitruvian man itself, despite having 4 arms and 4 legs, is chiral. It has mostly to first order, first approximation, that mirror symmetry. And that comes from the fact that it's part of a large group of animals, the bilaterians, who during development have this type of symmetry. They don't always keep it, but there are plenty of examples of animals around us that have this mirror image symmetry in them. You don't necessarily need a mirror symmetry. You can have achiral thing by translation plus rotation. For instance, if I take the figure 8 knot, and my last Gresham lecture, I'll talk more about knots, the figure 8 knot, and I take its mirror image, it doesn't have any obvious mirror symmetry, but if I can find an axis here along this line, and if I rotate it by pi, I can superimpose on itself. So the figure 8 knot is a mathematical object that has the property of being achiral. But mostly, there are plenty of chiral things also. Your left shoes, your right shoes, they're both separately chiral, gloves, hands, and interestingly, seashell. Here are two examples of Neptuna. One is left-handed and one is right-handed. And I brought you an example here. This is not a Neptuna, it's a Busicum. The third lecture will be about seashells, so if you like seashell, come back. They're full of incredibly fascinating geometry. So this one was given to us by the Oxford Museum, actually, because I thought it was splendid, but for them it was not particularly good. So this is a Busicum, so it's a knobbed whelk. And if you take the tip up, if you put the tip up, if the opening is on the right, that's what we define as a right-handed or dextral seashell. And if you're lucky to find a specimen or a species that has an opening on the other side, on the left side, then that would be a left-handed or sinistral seashell. They're actually very rare. We'll get back to that in a second. So I can define properly left and right based on where the opening is for this structure. There are also other mathematical objects that are chiral. The prime example among curves is the trefoil knot, the simplest possible non-trivial knot. If I take its mirror image, there is no way I can superimpose it. Actually, it's much stronger than that. You can prove, and it's quite difficult, that even if you deform it, even if it's made of elastic material, there is no way you can put one on top of another one. So there is a topological notion of chirality, but we're not going to talk about that. The prime example for us, or the gold standard, are going to be helices, because these are very simple structure. And on my right is what I call a right-handed helix, and on the left, a left-handed helix. So why do I call them like that? Well, it's what is called the left and right-hand rule. So I call the helix on the right right-handed, because if I put my thumb along the axis and rotate naturally my hand, just like I would do if I try to use a screwdriver, if I naturally rotate my hand, my finger would follow the path of a right-handed helix, like I show you. So this is known probably if you did any physics, it's known in physics as the right-hand rule. And Feynman says, we know that the right-hand rule was merely a convention, it was a trick. And I want to go back a little bit in time to see where this convention, or how do we call an object left or right, actually comes from, because it's quite difficult. So think about how would you describe what left and right is just in words, without pointing to your body, without making reference, without showing a picture, to, let's say, an alien. You know, they don't necessarily have hands or that. You have to define what left and right is for them. And it's quite difficult without pointing directly. And people have been struggling to find a decent definition, a fundamental definition, especially in physics. So where this left-right convention comes from, already philosophers in the 19th century, 200 years ago, were wondering about that. A young Karl Marx wrote, "Definition is lacking. Who shall define, who shall determine which is the right and which the left?" And I can only think that it's clear that the world would be a different place if Marx had continued his reflection rather than go on and wasting his time on politics and economics. Now, another bearded gentleman who was obsessed with chirality is James Clerk Maxwell. And around 1871, when he was making the final touch of his supreme theory of electromagnetism, he had a very anxious moment. He realized that there was a problem in his definition of left and right, and there was no proper definition. So, in a meeting of the London Mathematical Society, he gathered his friend, William Thomson at the time, who would become in 1892 Lord Kelvin, Arthur Cayley, the great mathematician, and others, and said the following: in pure mathematics, little inconvenience is felt from the one of uniformity. As long as you're consistent from one book to the next, that's fine. But, he says, in all physical sciences, it is of the greatest importance that one or the other system should be specified. And what does he mean by that? You can write the entire theory of electromagnetism, for motion of charge, for instance, in 3D space, using Thie's convention or Thie's convention. And why does it matter? Well, if you have a charge traveling in the direction A, and it's subject to a magnetic field B, it feels a force in the direction A cross B, which is up. That's physics, independently on anything. But that I use the right-hand rule, A cross B is the direction. So if I write a formula, I know it's in that direction. But if in another part of the book I use a left-handed system, then the force will be in the wrong direction. My formula will not be valid. So it's very important that one or the other should be specified. They had a long discussion, and we know the result because it was written in a little popular science journal called Nature. And what is the final word? It says at the end, in consequence, the right-handed system symbolized by a corkscrew, that I brought with you, or the tendril of the vine was adopted by the society. We'll get back to the tendril of the vine in a minute. So, very pragmatic, Maxwell tells you, in case if you have any doubt, go to your kitchen, find a corkscrew, and this is a right-handed system. That's great until you might come by chance to this corkscrew, which happened to be a left-handed corkscrew, and the entire theory of electromagnetism will fall because you got the wrong corkscrew. If you don't believe me, I invite you to have a look. This is a true left-handed corkscrew, which is very useful for left-handed to open bottles. And indeed, 2 years later, when he published one of the most important books of mankind, The Theory of Electromagnetism, absolutely beautiful, he writes in the first few pages the convention that he will use. And he says, Professor Miller has suggested to me that as the tendril of the vine are right-handed screws and tools of the hop left-handed, the two systems might be called tools of the vine and the hops respectively, which is interesting because out of the vine you make wine and out of hop you make beer. So it's the difference between beer and wine. The system of the vine which we adopt is that of Linnaeus and of screw makers in all civilized countries except Japan. So there is a lot to unpack in here in this statement. So first about screw. Well, it's true that most screws are right-handed. There are exceptions. The Inuit would use left-handed screw, for instance. But I could find in the last 25 years, since I first read this footnote in Maxwell's book, I could find no indication that people in Japan use left-handed screw in the 19th century. So if anybody out there has any reference, please send it to me. It's driving me nuts. Why would Maxwell think like that? But more important, he talks about tendrils again. And that rose my interest because I'd also work about tendrils, and we'll talk more about plants in my second lecture. Professor Miller was a famous crystallographer in Cambridge, but he was no botanist, because otherwise he would have known a little bit about the tendrils of the vine, and I'll tell you in a minute. And the last thing would be the system of Linnaeus that Maxwell talked about. But let me tell you about tendrils. So tendrils has this long modified leaf that some type of climbing plant used to grab a support and reach further heights. And here is how it goes. They do a motion called circumnutation, so they move around until they grasp a support, and then they start exerting tension. And here is a little movie. It's narrated by Attenborough. You can hear it, but I'll tell you what's going on. The tendril grasps a support and starts building curvature, in this case, and bring the tension. But what you see, the end result of tendrils, and you see any tendrils going around on any type of tendril-bearer vine, is that it has both right and left. So if you pick one, how would you decide what right and left is? Very bad idea. And it's a problem. Why do they have both left and right? It's a very interesting problem that was already studied by Charles Darwin when he wrote a very nice little book on climbing plants, in which he has this drawing by his son, Francis Darwin, which clearly show the left and right structure. It's a problem also that's been studied by De Vries around the same time, and De Vries is the father of genetics. And mathematically or physically, it's quite interesting, because if I take a naturally curved elastic filament under tension, I can do two things to it. I can increase its curvature, so I take a long elastic structure. I can increase its curvature. That's what happens with the tendril. It naturally wants to curl. or I can reduce the tension. But once the tendril grasps something, it cannot fully rotate one way to make a helix one way or the other one. The total rotation is always 0, so it has to balance between a left and right-handed structure. The net result, if you reduce the tension or increase the curvature, is to create an instability. And you can do that with telephone cords for young people in the audience. That's what your grandparents use to make, in the apparatus called a telephone, which used to make call for one person to another one. Well, here is a telephone cords that are fully uncoiled. And if I release it, I would naturally create left and right structure. Here is a little movie, same chords. And the net result is, by the end, I have a left and right structure. You can actually write a very nice little model of that. And together with my student at the time, Tyler Macmillan and Michael Tabor, we demonstrate the existence of this very universal instability. If you take such naturally curved structure as I show you and reduce the tension, it would form left and right-handed structure. But the interesting part for us is that a tendril is neither left nor right. So you certainly cannot use that as a convention for left and right. So the third thing that Maxwell mentioned is Linnaeus, the system of Linnaeus. So Linnaeus was the great and first taxonomist in many different species of animal and plant. In particular, in 1751, he published Philosophia Botanica, where he does this type of systematic taxonomy. And in there, indeed, he introduced and defined what left and right for plants and even show a picture. He said sinistrosum, like sinistrosum left, is this type of plant, Humulus, hop, Humulus lupulus, is hop. And dextrosum, here's an example, is bindweed or morning glory. It's an example of right-handed structure, very well defined. And page 103, he has again the same definition. He says humulus is that left-handed structure, and convolvulus is the right-handed structure. No problem, very consistent. Here is a problem. In the third edition, he had an erratum. Yes, it gets very detailed here. And in the erratum, he says, well, on page 103, I made a mistake. When I say right, it should read left. But it doesn't say anything about page 39. So depending on how you read the original and the subsequent text, you would have different definition. And this problem cascaded to the whole 19th century with different plant physiologists and botanists and all that having different definition of left and right. And you see plenty of them in the literature. You can be sinistrosum externe visus, so left view from outside, right view from outside, following the course of the sun, or like the hand of the watch, and so on. All that to say left-handed. It's a tough problem. For us, we're going to agree that the one on the left is a left-handed structure. And when you see it's easy because you can see the coil on your side going up with your left hand and the one on the right with your right hand. So it's very easy to recognize when you are obsessed like me about these things. And the problem is that even at the most fundamental physics, there was no way at the time of Maxwell to find a fundamental difference, an experiment for which you could distinguish left and right from its mirror image. But that came in 1956. It turns out that in our world, most processes conserve what physicists call parity. That means there is no way to distinguish in an experiment from the same experiment in the mirror world. There is no different physics if you completely inverse space for going from left to right. And that was the status up to 1956. People like Feynman and Pauli were convinced that there was conservation of parity to all of physics, up to the point where Ching-Chung Wu in 1956 made a crucial experiment and showed that there is one of the four fundamental forces of physics, the weak force, that does not conserve parity. Meaning that if you look at the experiment she looked at, it's cobalt-60, so she looked at the decay of cobalt-60 that sends electron and neutrino, and they come up with a given spin. And it turns out that the same experiment that would have been done in the mirror image, mirror world, would lead to a different outcome. And there was hence a fundamental physics difference between left and right that you can in principle define. And that was a groundbreaking experiment, one of the most important experiments, so important that in 1956, Yang and Lee received the Nobel Prize for experiment. But as Feynman says, the rule is that the particles which carry spin come out in weak decay with a spin mostly to the left. So you can make that difference. And we know now in physics, it's built in the standard model that the coupling between the electroweak coupling breaks the parity between left and right. But all other processes conserve the parity. It's not just in physics that chirality turns out to be important. You can find chirality everywhere. We talk a little bit about biology. In biology, you can see twisted trees going down the scale, twining vines, as we talked. This is a beautiful example. An umbilical cord is made of 2 arteries and 1 vein. And essentially, you either see left-handed or right-handed, or a mix between the two. I'll get back to umbilical cords and experiment you can do, or interesting things you can do with them in my last talk. And a little bit smaller, seashells, also either left and right, very well defined. If I keep going down the scale, here is the model organism Arabidopsis, a very not particularly nice plant, but the most studied of all plants for its genetic material. If you let the root grow in agar, they would make a definite right-handed structure. And if you zoom at that, you realize that the cell, the root is made of 5 cells that are helical around the cylinder of the root. And that, if you keep zooming, the cell itself has a definite handedness because it's made of cellulose that follow microtubule that zip around in an helical way along the cell, which also, this helical structure is what allows the cells to increase in size under turgor pressure. Keep going down the scale. Keratin, which we all have plenty of, it's what hair and nails are made of, is a well-defined left-handed braid. And that left-handed braid is due to the fact that it's made of alpha helices, a secondary protein structure, that is right-handed. And you can always ask the next, but why is the alpha helix right-handed? It comes from the chirality of the amino acid that it's made of. There is very well-defined chirality. Almost all amino acids have a well-defined chirality that we see, and not the other one. We'll go back to them. An interesting question is chirality transfer. If I know the amino acid a certain type, do I know that the alpha helix that I can make out is right-handed, and so on? If I know about microtubule, can I predict the handedness of a structure? How is symmetry at a given scale, a microscopic scale, is being transferred at higher and higher scale, all the way to the organism, for instance, and we have, for most people, a heart on the left side, for instance. And that's due all the way down to the chirality of certain type of protein in this case. Very important in biology, but also in chemistry. There is no place where it's more important in chemistry. And it's really Louis Pasteur that first understood that way before Kelvin and other one. In his text, he defines very well the notion of chirality. And back in 1848, he realized that tartaric acid salt are 2 different types of slightly different crystals that he could saw in his microscope. And a racemic mixture is one that's made 50-50 of a molecule and its mirror image. So he manually separated the mirror image crystal, all the left and all the right one, and then he realized that these 2 different forms interact differently with light. The polarized light would turn the plane of polarization one way or the other way. And that was one of the greatest discoveries of the 19th century, and the greatest discovery of Pasteur. Has been argued that all the subsequent discovery of Pasteur, like pasteurization and antibiotic, come from that first experiment and his interest in chirality. So we easily confuse, because we don't really use chirality that much in everyday life, left versus right, maybe for reading and things like that. But we definitely can't smell chirality, or nose is much better than that. And here is a simple example. This is carbon and its mirror image. And depending whether it's a right or left structure, it smells differently. One is the smell like oil of caraway, the other one smell like oil of spearmint. So it's very different in chemistry and biology. One molecule and its mirror image are very different in the way they interact with us. And the textbook example of that is in drug manufacturing, and it's the tragedy of thalidomide. So thalidomide is a simple molecule, a very interesting one, and in the late 50s and early 60s, it was prescribed to women in 46 countries because it was found that it was actually very good to treat morning sickness. And so many became pregnant. The only problem is that the toxic form, the mirror image, the toxic form creates childbirth defect. And maybe 10,000, possibly 20,000 women have been affected, and with a birth with 40% of death rate for them. So it was the worst tragedy, medical tragedy that was created by us, and it prompted the creation of a much more stringent scientific inquiry and process at the FDA in the United States that carried almost to these days, and we'll see if it continues in years to come or if other tragedy will unfold. So one of the solutions for this process is you can think, well, maybe if we isolate only the safe compound, we can give that to women or the patient. It turns out that this wouldn't work. This is such a simple and small molecule that it can naturally invert itself in the body and be toxic again. So in an interesting twist, in recent years, been shown that thalidomide is actually very good for treatment of some cancer. So the story of thalidomide goes on. It's something that was suspected or talked about a century before by Lewis Carroll. Through the looking glass, we have Alice that's look at her kitty cat and say, how would you like to live in a looking glass house, kitty? I wonder if they give you milk there. But perhaps looking glass milk isn't good to drink. And indeed, if you take lactose is a chiral molecule, and probably the little kitty wouldn't digest it very well. So it was very precise in a way. Okay, but let's go back to a little bit more mathematics about chirality, that we've seen how important it is in all aspects of science. There is a very interesting connection between chirality and the dimension space. So let me tell you what I mean by that. In one dimension, you can only have objects along the line. So the only thing that you can do is move the line over. So if I take a set, that little blue set, and I take its mirror image, I have another set. And in 1D, any connected set like that would be chiral, achiral, because I can always translate it back. No problem. If I take a disconnected set like this one, I get into trouble. I take its mirror image. I certainly can translate it, but I only live in one dimension. So there is no rotation. I would have to go to the other dimension to do a rotation. So a disconnected set like that is a chiral set in one dimension. However, if I look at the same set now in two dimensions, I take the set, but now I see it as a set living in a two-dimensional space. Here is the same mirror image, and I can translate, but now I can rotate because I'm in two dimensions, and so the same set is actually achiral in two dimensions. Okay? That's good warm-up. Let's go to 2D now. I take this spiral, its mirror image. It's easy to convince yourself, and the proof is not that hard, that this is a chiral set. If I move it back, translate, and try to match it, there is no way I can match one on the other one. So in 2D, it's clearly a chiral set. But if I look at the same set now in 3D, I can literally turn the page over and put it back on itself. So this set is achiral. So we reach an important observation, is that chirality depends on the space in which you look at, which is something that was already proved by Möbius in 1828, and Möbius showed that any set in n dimension that is chiral becomes achiral in n plus one dimension. And yes, it's the same Möbius than the Möbius strip that, as you can see, is also a chiral object in 3D, but achiral in 4 dimensions, which eventually the philosopher picked up after a century. And you can read in Tractatus that Wittgenstein says a right-hand glove could be put on a left hand if it could be turned around in 4-dimensional space. It's a nice way to put it. Okay, that's quite interesting. Now I want to focus more on 3-dimensional space, which is where most of the interesting things happen as far as our interaction with the world is concerned. And I want to talk about a problem, which is the problem of chirality measure. How do we measure chirality? Or even, how do we attribute left or right hand to an object? Here I was lucky, I can directly refer to left or right-handed, but there are other objects. So this is actually recent work that I've done with Adrien Oliveri, Derek Moulton, and Thomas Lessing, and we have a very big paper on the subject. So what about chirality? Well, we've decided that the helix on the left is a left-handed helix, -1, if I put a number, and the one on the right is right-handed, +1. Okay, now if I know that, do I know about the chirality of this potato? Is it left-handed or right-handed? Most potatoes are actually chiral, right? But is it left or right? What's the number that I can attach to it? Okay, or if I want to be more mathematical, what about this object here, which is a twisted trefoil? That's courtesy of Zebulon Goriely, my first son, who's also with us today. That's great. So he made this for me years ago, actually. And if I know about the helices, is that left-handed or right-handed? Is there a way for me to know? Okay? In order to understand that, let's go and do a little bit of geometry, or more interesting than geometry is differential geometry. If I take a curve in the plane, a smooth curve in the plane, I can look at a point P, and at that point, I can find the best fitting circle, just like the one that would really fit nicely. It's well-defined mathematically, no worries. It has a radius r, and if I invert this radius, I define its curvature. And curvature, the name tells you what it is. The higher the curvature, the tighter the curve. So if another point here where the curve is tighter, I have a smaller best fitting circle, the radius is smaller, hence the curvature would be larger. And what's important about curvature is that it assigns its value at every point on the curve, and is independent of the orientation of the curve or where it is in the plane. It's an intrinsic number, intrinsic function. And it's related to the first fundamental theorem of differential geometry of curves, which says that in the plane, a curve in the plane is defined by its sine curvature along its line. Meaning, if I specify the curvature at all points, I define a single curve up to a translation and rotation in the plane. And you know it's important in mathematics when they have the word fundamental in front of it. But in 3D is not enough. Now, if I take a curve in 3D, I need something else, and this something else is called torsion. And torsion measures what's called the variation of the osculating plane. So the best fitting circle in general fit in a plane, the one that I can best fit, but this plane can change. In 2D, the plane is already the same, but in 3D, that plane moves. And torsion measures the variation of that plane. If the curve is in the plane, no variation, so the torsion is 0. But the torsion changes as soon as I get out of the plane. And now the fundamental theorem of differential geometry of curve in space is that a smooth curve in space is defined by its curvature and torsion. That's enough to fully characterize. So that's a lot of work. Let me give you a simple example. The most simple are curves that have constant curvature and constant torsion. So what it would look like? Well, if something has no curvature, it's straight, as the word says. So no torsion and no curvature is a straight line. What if you just have curvature? If the curvature is constant and the same at all points, so it's the same at all points, the best fitting circle is itself, it's a circle. So no torsion but positive curvature, we define curvature to be positive, would be an achiral object. So what happens if now I fix constant torsion and constant curvature? I have two choices. I can either take negative or positive torsion, and that gives me either a left-handed helices or right-handed helices. And we're back to our nice helices, and you know why in differential geometry they are so important. They are the curves with constant curvature and torsion. And that gives us an idea, and the idea is that we can look at torsion to measure chirality. And here is an idea. I can take the sine of torsion, meaning the sine function is -1 if the torsion is negative and +1 if it's positive, and I can sum it all over the curve, but in continuous, I integrate it and divide by the length of the curve. And it turns out that a decent chirality measure, it's exactly -1 for helices that are left-handed and exactly +1 for right-handed helices. And on top of that is what in physics is called a pseudoscalar. That means it changes sign when you invert from one to the mirror image. If you invert the space, it changes the sign. So it means that if chi is different from 0, automatically the object is chiral. I have a way to measure whether an object is chiral. As soon as it's different from 0, I know I have chirality. But there is another problem. It is, what if chi equals 0? Does it mean it's achiral? Well, it turns out that it's not the case, and let me show you a counterexample. Here is a little curve that I cooked up. It's mostly made out of a left-handed helix on the left and a right-handed helix on the right. So this part is mostly a left-handed helix and then transforming to a right-handed helix. And they have different radii, which is quite important. So if I take a window and move along this curve of fixed length and move along this curve, I sample the curve at different places. On one side, I have the pure left-handed helix, and I move to the other side, I have the pure right-handed helix. So on this side, I have chi equals -1 when I apply the chirality like that. And you see the graph on the right side of the screen. I have -1 in chirality. And as I move the window, it's a smooth, continuous process. So I have every point of my window give me a different chirality, and I obtain a right-handed helix. The problem is that when I go to -1 and +1 with a continuous function, I always have to go to 0. So there is one point here where chi is 0. But the way I chose my curve is such that no window would pick up an achiral object. Because they have different radii, if I flip and look at the mirror image, the difference in radii makes sure that I can never superimpose them. And hence, this is an example of a false positive. It's called the problem of chiral connectedness, where there is, not for just that function, but you can prove there is no scalar measure of chirality. There is no way that would not give you a false positive for particle activity. So another way to look at the problem is to look at it slightly differently and see that chirality not something purely intrinsic, but the way an object interacts with the world. And I go back to this object, and I say, okay, it's hard just by the geometry of it, but what if I put it in the wind or inside a viscous fluid, for instance, I let it drop? Would it behave differently or turn differently in space if it's left-handed or right-handed? And can I use that to assign chirality? So if I take, for instance, a trefoil nut and I hand it by the tip like that, I'm always going to have the wind coming from the top. You can do experiment that was nicely done in this paper, and that it shows that it turns one way, just like that. But if I put it differently and put it the same wind, it's turned the other way. So just like Pastor did, and it's more than an analogy, it's actually very close, we can look at chirality of an object by the way it interacts with the world. And it's quite interesting because it not only gives us something to work on the geometry part, but it's the way it interacts with the world, so it's the way it builds block with the world also. That measure of chirality is directly related to its properties of interaction with the environment. So what is the idea? I take my trefoil nut and I apply a uniform field U. And what happens is that it induces an instantaneous rotation, omega, angular rotation, which is a vector that takes place around an axis. So flow is always coming like that. Depending on the orientation, it wants to turn, and that's the rotation omega along a given axis. Okay, so a vector U is related to a vector omega by a matrix Q. And you can show that this matrix is a pseudo matrix or pseudo tensor, because if you invert space, it also changes its sign. So what's special about it is that I can, in general, for an arbitrary rotation, my trefoil would wobble in space, because as soon as it starts moving, it changes orientation with respect to the flow, and then it starts wobbling around. However, there are distinguished orientation in space of my object such that it will rotate along the same axis, the axis. So I can try to find how should I orient my object in 3D so that it would only spin one way or the other along the vertical axis. And you can do that. Mathematically, it says that the rotation vector is the same direction than the field vector u, and that means that u is what is called an eigenvalue, an eigenvector with an eigenvalue omega. So if you've done linear algebra, you recognize the notion of eigenvalue. It just means the direction of my object so that it would only rotate along the vertical axis. And once I can show that generically it has 3 such rotations, and among these 3 rotations, it's either going to turn clockwise or counterclockwise. And all I have to do is count the number of times it turns clockwise or counterclockwise and use that as a definition of chirality. So it turns out that if it has 2 positive rotations in the same direction than the flow, the object we're going to call right-handed, and it has 2 negative eigenvalues, it's left-handed. And you can do that very easily now if you put all the mathematics together and show that the trefoil knot that I show you is a right-handed object because it has 2 positive eigenvalues. And Zebulon's trefoil is also a right-handed structure because it has the same geometry than this one, plus a right-handed helix built on the top, and you can compute the number accordingly. And so that gives us a different feel, a different way to capture this essential feature of chirality for simple objects. Now, the last things I want to do is, okay, we have a measure of chirality, but I want to go a little bit further. How would I induce chirality in an object? Or what I mean is control chirality. And this is really the work that I've been doing with my colleague in Stanford, Professor Alain and René Zhao, who did the experiments. And we had a student together with Derek, so a student in Stanford, Bartek, who just finished about a year ago now his thesis on the subject. So it was also done with my 3rd child, Zephyr. It turns out that Zephyr is a biologist and is an expert in elephant. So let me tell you about the elephant not in the room. What's special about the elephant is that they have, just like we have handedness, we have a preference for left or right, elephants have trunkedness. They have a preference for grasping object either turning left or turning right. And you can see that because of the way they use the hair and all that. And Zephyr specialized during his studies on elephants and went to Kenya and made this little movie for me of the elephant eating and plenty of other data that we've been using as part of the project. So let me tell you a little more about elephant trunks. They're quite interesting because the elephant, as you can see turning left or right, controls its chirality. It makes something that looks more like a right or left-handed heels. So how does it control chirality? So trunks are just magnificent organs, probably one of the very special organs that you can find in the natural world. They can be 2 meters long, diameter 15 centimeters, with nostril, the 2 black dots that you see there, about 3 centimeters. They are muscular hydrostat. They have no bones, but they have more than 90,000 muscle fascicles. And to give you a comparison, the human body might have about 60,000. So just in its one elephant trunk, it are more muscles than in our entire body that are organized mostly in 17 different muscle groups. And what's special about this is how they're organized. They're very structured. What you have are radial muscle that when they contract change the size and the diameter, so it allows it to control intake from the nostril. It has a giant longitudinal muscle that sits on top of its head, that's in blue, and that allows it to support the full weight of the trunk, right? By contracting, it can go up and down. But for finer control, it has this muscle group that you see in red and green that are mostly organized left-handed and right-handed. So these are going around the trunk. And by contracting them, the elephant is able to push on one side or push on the other side. So one question we had is that 90,000 is too much for us. We don't like computers and all that. What is the simplest possible design that you can think of that would mostly replicate to first order what the elephant can do? And so after a few different attempts, different type of structure, we say, let's really go to the simple. We're going to take that one longitudinal muscle and two helical muscle, one left-handed and right-handed, and look at a structure like that and see what it can achieve. And so the idea is to have something that is rubber-like, a structure, and it has these two bands of muscle, or the equivalent of muscle. So it turns out that there is something in engineering that's called liquid crystal elastomer, that they're quite flexible, and when you put a current through it, it warms up, it changes the molecular arrangement with them, and that provides an overall contraction of it. And so it does very much something you can control, like a muscle contraction. And so here, we have three what's called actuator, one the longitudinal one, and the two left and right. Contraction, we're going to assume, is uniform. That means it goes from, let's say, 1 or 2 meters down to a fraction of that. So we have three numbers, each of the actuation. So it's three numbers, which is the shortening of each of these muscle group or equivalent muscle groups. And the mathematical question is, how do you go from these three contractions that you can impose in your lab to the shape in space? Okay? It's a long story, a couple of PhDs and all that's not important. The thing is you can do it, you can fully solve this problem, and from the three actuators find the curvature and torsion of the object in space. Hence, you can start controlling it and decide on the type of motion that you have, and go to the lab of René, and do experiment. So in the middle, what you see are the theoretical solution and the experiment next to it. And the first thing we do is activate the longitudinal muscle. Since it has no chirality, what you expect is a chiral solution, which we just curl the solution, would be like that. Then you can start actuating the helical muscle, the one I think is the right-handed one, and then you create a structure that starts curling one way, as you see. And if you do both the longitudinal and the right structure, you obtain that. And you see the good match with the experiment compared to the theory. You can also go back to what is known about elephants. And there is a very nice paper that studied different modes of deformation, looking at some way of following the motion and the shape of the elephant trunk. And what they discover is that there are particular modes that are repeated by modes of deformation that are used by elephant. And we could show that with these three different actuators, you can actually very easily actuate this principal mode of deformation. So despite the fact that it has many different controls, you can fully reduce this problem and understand how the elephant controls its own trunk. But of course, you want to go a little bit further, and you want to see more specialized motion. And here are pictures as the work with Zephyr, and different type of mode of interaction, of feeding, or scratching, and so on. And so we decided that we needed a better model. Instead of in one section, in principle, we could have multiple sections. We haven't done the experiment, but we do the theory of that. We have multiple sections of an elephant trunk that can all be actuated with different layers inside. And so the trunk 2.0 has 15 actuators now, but it can do wonderful things. Since you can control the shape, you can see, you can decide on certain motion and find the actuation that you need to do this motion. A first one, simple one, have a log and try to grab the log and move it up, right? And our digital trunk is very happily does it. It's a very tough problem because you have to take into account the contact and all the mechanics and the self-weight and all that, but it can do it. But more important than pulling log, that's just for the pleasure of humans, elephants have to feed themselves, and again, you can put that as an objective, and the elephant happily feeds itself. And it's worked hard, it can feed itself for a long time if you keep putting food in front of it. And so now we have the ability of this structure to control the way it changes in space, and that applies not only to elephant trunk, but also to soft robotics, to plants and other systems. So to finish, I want to leave you with a few puzzles for you to think. We can have grand conclusion, but more interesting, I want you to take home a few things to think about. First, in your bathtub, I want to ask a simple question. Which way does it turn? So if you take a bath and pull the plug, you'll see the water swirling. And we taught in physics that due to the Coriolis force, it should turn counterclockwise, at least in the northern hemisphere. And that's what you see in the picture. So next time you take a bath, pull the plug and see if it's true, and think about which experiment you do so that to prove it's true, and what is the magnitude of the Coriolis force in the size of your bath. So think about it. It's a very interesting problem. It's not trivial. And experiments have been done, and be happy to talk about it. So that's my first one. My second one is really going back to Gresham. This is a drawing from Hooke in 1678. So Hooke was, before Sarah, the Gresham professor of geometry, many professors before. And you can see his fake portrait looking at us there. We don't know what he looked like because there is no surviving portrait of him. But we all know, if you've done any type of physics, about Hooke's law. And Hooke's law say that if you put a weight in this little basket, it would extend by a little distance that is proportional to the weight of the ducky that you put in there. Okay, fine. But the part that's left out of all your physics is that the basket, as you put the little duck in, might turn. So would it wind or unwind? Would the helix open itself or tighten itself? Or not at all? Possible choice. Right? A simple problem that probably missed by physicists for quite a long time. And the solution of it is quite interesting and unexpected. And why it's important, not just for spring, but it's also very important, for instance, in biology, because DNA also feels tension at some parts during the cell, and due to that, it can rotate either left or right, one way or the other, and as a result, open itself and have the ability to do transcription. So you'd better know if it opens in compression or if it's open in tension if you want to start understanding the basic molecular biology. It's a problem that I looked at years ago with my PhD student, Bojan Durikovic, and my colleague, John Maddox, who is at EPFL. The answer is there, but I want you first to think about it. And talking about DNA, let me go back to the interesting problem. DNA is mostly right-handed, despite the fact that not a day passes when you see a picture in a newspaper or left-handed DNA, because people don't pay that much attention to that. But why is it right-handed? There is a version of DNA called zDNA that is left-handed, but it doesn't look like that at all. This is bDNA, that's the main thing. So why is it right-handed? It turns out that the different bases are mostly planar, so they're all chiral. The reason it's right-handed is the sugar that it's used as the main building block within the DNA, not the base itself. And the same is true for protein structure. The alpha helix is a right-handed structure because it's made of a type of chiral molecule. And if you put them together in interaction in simple geometry, you'd see that the minimizer of the energy is a right-handed structure. That's fine, we understand that. But why in the world do we live in a world where we have this type of sugar and now the chiral image of it, and that type of amino acid and not the image? We only live with one type of biology and not its mirror image. It's the problem called of homochirality. It's a problem that was already raised by Pasteur, by Curie. It's one of the most fundamental problems of biophysics, if you want, is what is the fundamental origin of this chirality? Is it the weak force that has this slight difference, so something at the level of 10 minus 10 meter, or is it polarized light that comes from galaxy, 10 to the 10 meters? We don't know. So it's something interesting to think about. Another little puzzle comes with seashells. Gastropods like this one are mostly right-handed. 90% of the species, 95%, are right-handed. But ammonites, which are mostly extinct, so cephalopods, in particular ammonites, they're all extinct, the ammonite, but Nautilus and all that, are mostly achiral. So what is the fundamental difference between these two groups of mollusks, one that is mostly chiral and the other one that's mostly achiral? What is the fundamental reason for that? And I'll get back to that in my third lecture. And talking about seashell, I gave the last words to Darcy Thompson, who wrote a wonderful book on growth and form, was the first to interrogate nature in terms of geometry. And in there, he writes, why in the general run of shell all the world over, in the past and in the present, one direction of twist is overwhelmingly commoner than the other? No man knows. And I'll leave you with that reflection. Thank you.